Well, hello everyone. I'm 𝗥cie𝗱𝗆, technical coordinator of 𝗥cie𝗱𝗃, and very glad to be here today. We have a talk from Mr. Rocky Roden, and we're all looking forward to that. Thank you for joining us. So before we begin, I think we probably have some new participants at our event today. So I would like to just quickly share a few introductory slides about Evolve for those of you who aren't familiar with it. So of course, this is our Fearless Explorer Fridays. This is when we meet with our teams every week for Evolve during the 6-month virtual internship starting in January and going through June. And we use some of these Fridays as an opportunity to bring in some top industry experts like Mr. Rocky Roden. So for those of you who aren't familiar, Evolve is a 6-month part-time virtual internship for students. It is collaborative and it is global. We have teams this year all over the world from Boise, Idaho, down to Rio, all the way to Malaysia, China, and Indonesia. So that's the teams this year. And what we do in Evolve is we teach the skills necessary to be successful in a multidisciplinary, real-world digital E&P setting. That's a lot of words, and it's a lot of stuff that we basically teach. And the key thing is that the students get the chance to work with highly experienced mentors like Mr. Mike Forrest, who's here in the room, people like Miss Jenny Thompson and others, and that's the way they learn. Anyway, a few pictures from some of our Zoom meetings, and that's the picture of this year's teams. We're strong believers in the importance of geological thinking. We're going to talk about this slide a little bit later. And I like the slide because it shows a couple of things. This is one of the maps from one of this year's teams, and that's a pretty nice map there. And there are even people sometimes after years who don't get maps this nice. So this is good. That's showing the progress of our teams. We have a little philosophy here, which is if you understand it, you should be able to draw it. And I'm talking geology here, of course. And if you can't draw it, you probably don't understand it. So these are some cartoons from different parts of the Gulf of Mexico, mentor cartoons. And this is showing you some cartoons prepared by the students and to show you that they're coming along and learning. So anyway, Evolve is a great experience. And it was founded by Halliburton originally in conjunction with SEG. And now we have a lot of other companies contributing software, including a company here with Geophysical Insights that Mr. Roden works with very closely. And this year, which is our 3rd year of the new Evolve, you can see here that we've had universities from all over the world, that's the red dots, and the participants in those universities really span the globe. So it truly is a global program, and again, it's collaborative. And by the way, if any of you who are in companies, 0 to say 5 years of experience, and you wish you could have an Evolve type experience working with real world data and having a lot of very experienced mentors working with you, almost as an extension of your company, well, the good news is we have Evolve Professional, and you can follow up with us on that. We have lots of information. Go to our YouTube channel, LinkedIn, and our Facebook page if you want to learn more. So that's it for me. So I would like to, I'm going to stop sharing here. I would like to introduce Mr. Rocky Roden here. And I've known him for a long time. And I think Mr. Forrest has known him probably even longer. But he began his career, was Maxis the first place you began your career?
Actually, I worked on a seismic boat and then pogo producing back in the 80s.
Okay, because I went to your LinkedIn page and I think Maxis Repsol is the first place. So anyway, but yeah, we all paid our dues, didn't we, sometimes on those boats and in the field. But anyway, so you were at Maxis and then Repsol and ended up as chief geoscientist of Repsol, where it tells me here you had 250 geoscientists reporting to you. You must have had a lot of performance reviews to do.
Well, some of them not so directly.
Okay. So anyway, you've published many papers. You and I were on the SEG Leading Edge editorial board. I forget what years did we overlap. Was it 98, I think, or?
Yeah, 98 to 2002, somewhere in there.
Yeah, so those 2 years we overlapped. And then since then, you were a consultant with SMT, Seismic Micro Technologies, who came up with the Kingdom software, so very familiar with that. I think you worked with Mr. Forrest here for what, a couple of decades at least on the DHI consortium.
Yep.
And continue as an independent consultant, working a lot with the Paradise software and other tools. So anyway, welcome, and we'll turn it over to you to share your screen. So thank you for joining us today.
Yeah. Hey, I want to thank Alan and Mike for allowing me to give a presentation today. You know, I've been, as Alan indicated, an interpreter most of my career, whether it's doing the interpretation, managing interpreters, consulting with companies in interpretation and technical issues. And I've actually been doing machine learning for quite a while too. And so this presentation is from the perspective of an interpreter, not a data scientist, but from an interpreter who actually uses the technology and machine learning from a practical perspective. Now, we've all heard a lot of these terms: deep learning, machine learning, artificial intelligence, every day in our lives. But from our perspective as geoscientists, how does all of this technology relate to finding oil and gas? And hopefully we're going to go over and explore that this morning. So why use machine learning? Well, first of all, it can analyze a lot of data simultaneously. It's our big data issue. And we do have a lot of data, especially from the seismic perspective. It can determine relationships between different types of data. And now we can look at 2D cross plots, we can look at 3D cross plots, but if I have 5, 10, 15, 20 types of data, it's very difficult to analyze and understand how they relate or don't relate to each other without using some sort of machine learning. We can discover nonlinearities in solutions. A lot of our theories, a lot of the ways we visualize, interpret, and try to understand geology are based on linear assumptions. A lot of the Earth is not linear. Machine learning can help us understand that. Certainly, it can improve efficiency and accuracy over time. And of course, once we start applying these methods, it can get into the automation mode and help things go much, much faster. And of course, from an interpretive perspective, we're trying to interpret geological features and properties or trends that are very difficult to interpret or not even seen at all in conventional approaches, and ultimately reducing the risk when we drill a well. Now, data itself, as we know, is evolving to provide superior results, a lot of times better than algorithms, or at least the algorithms we've developed. In fact, if you think about it, why do you think Amazon and Google and Facebook and all these companies fight so hard to host your data for free? Well, it's not because they particularly like you, it's because they want your data. It helps them in their business strategies. But the real question is in machine learning, because they apply all that information in the machine learning approaches. But the real question is, can it really address the questions you're answering? Machine learning, actually, the computation of it is very simple. There's a lot of computations, but the math behind it is actually very simple. And it's the data and the amount of data that builds complexity, but doesn't really answer what I'm looking for. Now, one of the things as geoscientists we have to deal with is that geoscience is deeply grounded in physical laws and principles discovered by the scientific community over hundreds of years and by many of the individual pictures you see on the right there. Geoscience features have space and time relationships. They're very highly multivariate. They're nonlinear. They show non-stationary characteristics, and they often involve rare but significant events. Very, very difficult to interpret at times. And our data itself, our geological and geophysical data we use to interpret the Earth, have many challenges as far as resolutions, various degrees of noise, incompleteness, sample sizes, and improperly processed data, just to name a few of the things that we have to deal with making these interpretations. So how can geoscience interpreters ensure that the established physical bounds and rigorous theories that we've developed over these centuries are not violated? By the same token, how can we as geoscientists advance our interpretation methods if we're restricted by the established practices? Well, the solution to that is actually pretty easy. In the oil and gas industry, the proof is in the drill bit. When I drill a well, do the results come out as I predicted or as I interpreted? And I want you to think about it. If we knew everything in the Earth, if all of our established practices were accurate, we would never drill a dry hole. And of course, we know that's not the answer, not the truth. So what is machine learning? I've talked about it, but what is machine learning? Well, machine learning was coined by Arthur Samuel at IBM back in the late 50s. And he said it's the field of study that gives computers the ability to learn without being explicitly programmed. And we know that over the last few years, they've had machine learning computers, that programs that beat the chess champions of the world and other sophisticated games against humans. People don't realize that back in the early 60s, Arthur Samuel developed an application on the initial machine learning approaches that beat the checker champion of Connecticut. Now, I'm not sure how many people in Connecticut play checkers, but he developed a program that beat him. So this is when machine learning really started to evolve. Now, this is kind of I call it spaghetti bowl. This came from SAS, but then different sorts of categories of data science. But what I want you to look at is where machine learning is situated. It's a part of AI or artificial intelligence. And of course, artificial intelligence is any technique that enables computers to mimic human behavior. A subset of our artificial intelligence is machine learning. And as Arthur Samuel said, it's a technique that gives computers the ability to learn without being explicitly programmed. A subset of machine learning is deep learning. You may have heard this term, and I'll explain to you what that is in the next few slides. But Google machine learning, you would get something like this. These 4 different types or categories of machine learning. The most common type of category is supervised learning. And what that does is it takes a known set of data and descriptions of something, and you build a model, because I know what the answer is. I build this model from all these descriptions of whatever I'm trying to define until I think I got a good model that tells me what I know what the answer is. I take that model, apply it to another set of data, and hopefully that model will tell me what I was trying to find. This is supervised learning. And I'll talk about that, all these in just a minute. Unsupervised learning is very different. It knows nothing about your data. In fact, what it does is it goes in, looks at the data, starts identifying natural patterns and cluster structures in your data, and knows nothing about it beforehand. Very, very different approach. Semi-supervised is nothing more than combining supervised and unsupervised learning. You're starting to get much more sophisticated in the approaches and solving certain problems. And the last one is reinforcement learning, where you have an algorithm that learns over time and maximizes returns based on whatever the algorithm you're using, and then it does this over and over until you constantly improve and get the best answer. So these are the 4 basic categories. Now, supervised and unsupervised learning are the fundamental applications being used in our industry, at least in the geoscience part of our industry today. And I'm going to go over those. Now, if you look at supervised learning and unsupervised learning, here's a list of the different types of these machine learning approaches. There are certainly many more than this, without question. However, these are the most common applications of machine learning I have seen used in the interpretation community. If you look on the left under supervised learning, there's a whole set of red items, linear regression through support vector machines. These are not neural networks. These are different sorts of regression and classification approaches. They're almost statistical approaches, in fact. And then you have a supervised learning neural network approach. Under the unsupervised learning, we have neural networks, which are very different than supervised learning neural networks. And there are different types. And there's something called dimensionality reduction, and I'll talk about that in a minute, that you have to deal with. So if you look at these supervised learning approaches that are not neural networks, here's a list of them, from linear regression all the way through support vector machines. And several years ago, I saw this, and people were starting to call these applications machine learning. Well, I can tell you that linear regression, logistic regression, decision trees, I've been using those for years. And in fact, I know any interpreter that's been around for several years have been using these sorts of approaches before we started calling them machine learning. In fact, one of the fundamental ways we use it, and Mike Forrest probably talked about this last week, is an AVO interpretation. We will look at how amplitudes change with offset on a gather based on some sort of a Zopert's approximation. We measure or put a straight line fit or a linear regression fit through those data points to measure the slope for the gradient and the zero intercept, or the zero offset for the intercept. These are the fundamental attributes in AVO that we use every day. Linear regression, a very simple form of machine learning. And a very interesting presentation was given by ConocoPhillips, where they were looking at 40 surveys in their fields in the Gulf of Mexico and the North Sea. And 40 surveys, if you're not familiar, they shoot different 3D surveys through time, trying to see how the fluid and lithologic properties change with production. Well, what they determined is that inversion, even with all this well control, was not sufficient to really see changes in the reservoir through time. So what they did is they applied random forests and gradient boosting, and it would enable them, they integrated that with 40 seismic attributes and pre-stack data, and it enabled them to predict the change in pressure, water saturation, and gas saturation better than they were getting from inversion alone. Again, a very nice application of machine learning. But neural networks are really the foundation of the workhorse, if you will, of a lot of our geoscience, and especially our geophysical and seismic data. And of course, these biological neural networks, from which neural networks are based, relates to all these 10 billions of interconnected neurons, for example, that are in our brain. And each of these cells use biochemical reactions to receive, process, and transmit information. And of course, our artificial neural networks are nothing more than a computational simulation of the biological neural networks. And as I indicated before, we have two fundamental base types: supervised neural networks and unsupervised neural networks. And they're actually quite different. Okay, I've got a test. I know you're all students, you're probably sick of tests, but this is not too difficult. Look at this display here and tell me what the answer is at that question mark. Hopefully you got 81. Well, if you did, congratulations, you have successfully accomplished supervised learning. So how did you do that? So you looked at the numbers on the left. You saw if you square them, you got the numbers on the right. So you built a model. You applied it to the 9, and you got the answer of 81. A very simple, straightforward example of supervised learning. Here's another way how it's really done. If you have an object, in this particular case, a cat, you know it's a cat, and you have various labels or descriptions of that cat. And you put all these labels and descriptions together to build a model that tells you when I have these descriptions in this building of this model, I have a cat. From a geological perspective, perhaps say I'm looking for porosity. I look at relationships to permeability, maybe relationships to fluids, production rates, things like this. Those could be labels or descriptions that you build a model with. So you build a model that tells you, all right, given this model in this example, I get a cat. You take that model, you apply it to another object, and it tells you whether it's a cat or not. Very simple, very straightforward. So what are the pros about supervised learning? Well, it's very clear objective. You're telling it what to find. It's easy to measure the accuracy. It's very controlled. Now, it can be quite labor intensive on the cons side and limited data to work with. And the reason is you have to build or get enough labels and descriptions to build a model that will give you an accurate and correct answer. And you really have limited insights. You're telling it what to find. If I'm telling it to find porosity, it's only going to find porosity, nothing else, because you're telling it what to find. Now, I mentioned earlier deep learning. Well, if you look in the upper left display here, this is a very simple, basic neural network. And in fact, in today's world, they call that a shallow neural network. Well, you have some input values, then you have these neurons, which is in that hidden layer, and then you get to the outputs. And obviously, it's weighting these things back and forth in this model until you get an answer. If you look on the right, that's a deep neural network. And what distinguishes that is the fact that I have many hidden layers, as well as many neurons, but it's really having more than one hidden layer makes this a deep neural network. I have many, many weighted relationships between all these neurons, much, much more involved, a deep neural network. And on the bottom is the most popular deep learning network approach used today, certainly in our industry. That's convolutional neural networks. And this is based on image processing. Again, it's a deep neural network. So I'm going to show you an example, a case study, if you will, of supervised learning where we're using deep learning, convolutional neural network. Here's an example of a seismic line. And I have different reflection patterns that are on the seismic line. Quite often we will call these seismic facies, but I like better that they're different reflection patterns that mean something. Stacked channels, layered sediments, tilted fault blocks, whatever they are, they represent reflection patterns, hopefully associated with geology, but not always. In fact, the multiples is a processing phenomenon, but you can identify those. So I want to identify these with convolutional neural networks. Well, what I do is I pick these examples as labels that go into the model. So I go through, look at several lines in a 3D survey. I pick these different facies, if you will. It starts to build a model. I have a model, then I apply it to the whole 3D data set. Then ultimately, we'll have a three-dimensional display, which I can visualize, of each of these different facies that the convolutional neural networks has identified through the whole 3D survey. This is deep learning for seismic facies classification. Okay, I have another test here. And look at these 6 objects. And very quickly, how can you group these objects? How many patterns or clusters can I get out of these 6 objects? I won't waste too much time, but one way is shapes. You have round versus a box or a square. Another one is fruit versus non-fruit. Another is color. You can break these out by different colors. Well, congratulations, you have successfully accomplished unsupervised learning. All you did was look at these objects and saw how they grouped or what patterns they formed, or clusters, if you will. Unsupervised learning. So here's an example. If I have a lot of data, I know nothing about this data. I will apply an algorithm to it, a neural network, unsupervised neural network algorithm, and it will start to identify the patterns in all that data. No prior knowledge of the data at all. And then hopefully the output will break out the information into its natural patterns and clusters from the data. This is unsupervised learning. So what are the pros? Well, it's very fast to start. You don't have to do anything. You don't have to know anything about the data. Unlike supervised learning, where I have to develop all these labels and descriptions for the model, you don't do that here. It can be very disruptive because it is not going to give you necessarily an answer that you know that you're going to get. It's just looking for the patterns in the data. What are the cons? Well, it can be difficult to measure the accuracy at times. It can require more experience because you have to interpret the results. You're not telling it to find a specific answer. You're going to get a set of different answers. And then there's this thing called the curse of dimensionality, something we have to deal with in this sort of approach. So what is it? What is this curse of dimensionality? Well, it relates to something that we have to deal with when we're looking at a lot of different types of data or several dimensions. In other words, as the amount of different types of data or dimensions increases, the volume of space increases very fast also. So what's that mean? Well, if you look at this particular graph or this display, on the left you have a 1D plot, and I have a set of data points. If you go to a 2D plot, right next to it with the same set of data points, you start to get more space in between the data points. If you go to the 3D plot of those data points, a lot more space between those data points. So as the number of data types or dimensions grows, the amount of data required to analyze it grows exponentially. It gets more difficult to analyze what you have when you get a whole lot of data points if you don't have enough data to fill up that space. So how do we defeat this? How do we defeat the curse of dimensionality? Well, prior knowledge certainly helps, but what we want to do is reduce the dimensionality. It helps the overall process and gives us a more distinctive answer. So what we do is we tend to look at the data in the part of the data space where the data is most dense, where most of the information is at, and we ignore the parts where this is not present. So how the heck do you do that? Well, the most common method to do that is principal component analysis. You hear the term PCA. This is certainly the most popular. It's not the only way, but it is certainly the most popular dimensionality reduction approach. So how does that relate to us? Well, what this principal component analysis does, it's a linear mathematical technique that reduces a large set of variables, for example, a lot of seismic attributes, to a small set that contains most of the information from the large set. In other words, it can help us find out what are the most prominent attributes in this particular case. For example, if I have 2 attributes, and this is how they cross plot, what is the largest variation in the data? Well, as you can see very clearly, it's that red line. That's the first principal component. That's the biggest variation in that data set. What's the second biggest variation? Well, it's orthogonal to the first one, and it's the second principal component. I have two attributes, I have two dimensions, so I have two principal components. And you hear terms like eigenvector, which is nothing but the direction of these principal components, and eigenvalue, which really is the measure of the variance of each of these principal components. So how does that relate to interpretation? Well, here's an example. I had 12 seismic attributes, and I ran principal component analysis. And what you're looking at on these bars is the highest eigenvalue on each element in this survey. And say, for example, that red bar represents a line runs right through a well, right through a zone of interest I'm trying to interpret that has pay. Well, here is the plot of that. You can see the highest eigenvalue, which is that red, the measure of the highest bar in red. And I got 12 attributes, and what you're looking at is the percent contribution of each of those attributes to that first principal component or the highest eigenvalue. And it is very, very clear that these four attributes are very prominent in the data. Those four attributes are over 90% of the contribution of the highest eigenvalue. They're very prominent. But if I look at the second principal component, there are three very prominent. Now you can take, one method is to take those 7 attributes from the first and second principal component and take those into a unsupervised learning approach. Or you might take just the top one, the 4 very strongest ones you see at the top. There are different methods to pick these, but the bottom line is dimensionality reduction, reducing all these attributes down to a more workable data set to look at. So once you've picked, in this example, the attributes you want, you can take these prominent attributes and take those into an unsupervised method, for example, self-organizing maps, which is, we call those SOMs. This is an unsupervised learning method. Self-organizing maps, again, are an artificial neural network using unsupervised learning. And again, it looks at the data, classifies the data in categories, clusters, or patterns based on neurons. The neurons look in the data and identify these different properties. And a neuron is nothing more than a point that identifies one of these clusters. From an interpretive standpoint, the reason we look at this is some of these clusters identified by these neurons are going to have geologic significance. There's no question. The other thing is they will also see noise. Coherent noise, incoherence, it's just another pattern. That's good. If we can see it, we can filter those out at times. So how does this SOM work? Well, if I have a data set, and I have a very specific zone of interest that I'm looking at, I'm either defining it by time, above and below a horizon, or between two horizons, however I want to define it. I can identify this zone. And I can run principal component analysis on a bunch of attributes. And if I come out in this case, I had 10 attributes I thought were very prominent in that zone of interest. So every data point in that zone of interest has 10 values because I have 10 attributes. So I take all of that data at all the different scales, and I put those in something called attribute space. I have 10 attributes, so I have 10-dimensional space. I can't actually see that because it's beyond 3 dimensions, but mathematically, that's not a big deal. The first thing I do is to normalize all those data points. All those data points are now put on the same scale, and then I will put a set of randomly located neurons in all those data points. And then I say, all right, self-organizing map, find the patterns or clusters, and it will. And it will find, every neuron will find a pattern or a cluster in that data set of those 10 attributes that have been normalized. And then it nonlinearly takes that back to a 2D color map that has topology. As a geoscientist, we can relate to that. And what that means is that each of these hexagons represents a neuron that found a pattern. And the neurons that are closest to each other are more similar. Their patterns are closer to each other. That means something, especially from a geological perspective. And then I can interpret now, based on the colors of each neuron, how these patterns evolve and form from a geological interpretation perspective. So here's a case study, an unsupervised learning case study where I used principal component analysis and self-organizing maps. It's a very simple example of a very shallow, relatively shallow reservoir. It's in a bright spot world, as Mike has probably talked to you in previous presentations. It's a class 3 AVO settings. Amplitudes typically are associated with hydrocarbons. But before these two wells were drilled, which found about 100 feet of gas and oil, 7 different prospects were drilled, all of which were drilled on amplitudes, all of which found were either wet or low saturation gas. So the objective here was to try to find the most DHI characteristics and reduce the risk. We ran principal component analysis on 20 instantaneous attributes. And I specifically looked at this range of inlines in red through my zone of interest. And I plotted, as you can see here, the first, second, third, and fourth principal component. And I took the top 2 highest contributing attributes in each one of those principal components. And I came up with these 8 attributes. So based on principal component analysis, I took those attributes and started to run a self-organizing map. And these are the results. What you're looking at the top there is the top from this reservoir. That's the regular amplitude data, very good amplitude. You can see it very clearly. You can see amplitude conformance to structure. It's relatively consistent. It looks very, very good. Now, if you look on the bottom display, you're looking at the results from the self-organizing maps. Because one of the things in the self-organizing map computation is it also looks at how well the data points are related to the neuron that describe the pattern that it sees. If the points are very close to the neuron, it's high probability. If the points are very far away, it's low probability. And in this particular example, you see in the bottom left, that color map is there's 25 neurons. Well, what we found is that when I had less than a 1% probability, you see all that area in red, which corresponds more directly with the amplitude that relates to the top of that reservoir. That's because what we have found is that when the data points in attribute space don't fit very well or very anomalous to the winning neuron, they tend to be corresponding with direct hydrocarbon indicators. I mean, a direct hydrocarbon indicator is by definition a seismic anomaly. So they're anomalies. They're odd. And we see a nice correlation there. This display is a dip line running right through that field. And the upper display is the conventional amplitude data. You can see where the field is defined. The bottom 2 displays on the left are the results from the SOM analysis. And what happened is the neuron 20 and 25, which is outlined in gray, represents that reservoir above hydrocarbon contacts. And neuron 15, which is a reddish color, has identified the gas oil contact and the oil water contact. And if you look down dip, there's actually an undrilled anomaly down there that looks very prospective. It's too small, so it hasn't been drilled. And then on the bottom display on the left, you can see only those 3 neurons identifying that reservoir in the contacts displayed. But I also want you to look at that dashed box. That is at the very edge of that reservoir. And if you look in the upper right, the amplitude, you don't see a lot of distinction as you go from the hydrocarbons in the reservoir to the water leg. However, in the bottom right 2 displays, you can very clearly see where that reservoir in gray is pinching out. In fact, it's getting down to about 2 samples, well below the seismic resolution of amplitude data. Again, unsupervised learning giving you a lot of details in the data. This is the same analysis, but now you're looking at the strike line. And again, you can see very clearly the reservoir I've defined by the two neurons in gray, the contacts, gas, oil, or water contact, defined by the neurons in red. So I've talked to you about supervised learning. I've talked to you about unsupervised learning, but probably the real future is in semi-supervised and reinforcement learning. An example of semi-supervised is if I'm looking at a data set and I want to find out where the faults are located, the best way to interpret the faults. One way might be to take a set of geometric attributes, for example, curvature, coherency, similarity, various types of these that are very, very good about seeing faults, run those through a self-organizing maps, which produces a volume that is very, very good at seeing faults. Then I run a convolutional neural network over that data set that's very good at seeing faults. So I'm combining a unsupervised method with a supervised method to get the optimal results. Now, what you're looking at here is a display or a listing of what I have found over the last 2.5 years are the most common machine learning approaches in interpretation. The ones in red are supervised methods, and the ones in blue are unsupervised methods. There are certainly many more than these, and certainly there are several being applied in processing, seismic processing. But from an interpretive perspective, I found these to be absolutely the most common approaches being employed today in the interpretation community. Lithofacies interpretation, fault delineation, fault and fracture detection, stratigraphic facies, etc. Now, we do know that we're already starting to see higher resolution results with supervised and unsupervised approaches than for conventional methods of inversion, fault delineation, and stratigraphic facies. We're seeing better resolution than our conventional amplitude data can see. We are also starting to see potential direct hydrocarbon indicators, as I showed you previously. In fact, the display on the left there is a series of different AVO attributes that were used, and the low probability zones were in the white there, identified exactly where the pay was located. The display on the right shows you that these neural network approaches are even identifying noise in our data. This is at the top of the Eagleford Shale, and what you can see there in the red are acquisition footprints in the data, never seen on the amplitude data. But it's very clear. This is 10, 12,000 feet down a section. Machine learning was seeing it. And again, semi-supervised and reinforcement learnings, I think, is where things are evolving to. We're going to start combining these different approaches and getting better answers. So my last slide to make a prediction. This is my prediction, nobody else's. One is the machine learning is a disruptive technology. I think that it truly is. We're seeing things we've never seen before. And we have to try to understand it and employ it in our interpretation processes. Artificial intelligence and machine learning will not replace geoscience interpreters. I firmly believe this. I've been around for a long time. And I truly do believe that every time a new technology evolves, it doesn't decrease the amount of geoscientists, it actually increases the need for them. They have to employ methods, they have to employ that technology. We can do more, we can see more, we can get better answers. However, I do think the geoscience interpreters who don't use machine learning will be replaced by those who do. I firmly believe that's what's going to evolve, so to speak, in our industry over the next few years. Thank you very much. And I think Alan wanted me to comment on the pie chart there. And I think it's a very good one, describing today's categories of knowledge experience versus workstation workflows, software mechanism, tenacity and resilience, and curiosity and creativity. My comment on this is that I think that in the future, with the evolution of machine learning, that you're going to see the software and delivery actually decrease. The majors are already pushing very hard for a cloud solution, trying to eliminate a lot of the issues related to software delivery and how they use it. I think workstation workflows will start to be even more important as the older generation of the demographics start to go out of the picture and you younger folks start to take over machine learning. You need to take the knowledge that was developed from the old veterans and employ it in workstations to get better answers. So that's kind of my perspective on that. And with that, I'll give it back to Alan.
Okay, well, thank you very much, 𝗥cie. You want to unshare your screen?
All righty.
And I guess we'll give you a virtual round of applause here. Okay, so we have the students who are part of Evolve, who are participating through Zoom. You can put your questions in the chat that I will be able to see. And we also have some participants via YouTube and Facebook, and I believe they are going to send their questions such that our director, Mr. Mario Bainas, can see them, and then he's going to, I guess, either post them in the chat or let me know in some other way. So I guess I'll ask, are there any Evolve students who would actually like to ask a question in person? Since you're live, you can actually interact with Mr. Roden directly. So
yeah, Mr. Allen, may I ask a question in chat, or I can ask it in person?
No, please ask it in person. And the only thing we'll ask, by the way, is that each of you introduce yourselves by name and mention which university or team you're coming from, so Mr. Roden knows your context. So please go ahead. Yeah.
Yeah, thank you, Mr. Allen. My name is Alexander. I'm from Moscow, 2020 team. And I'm a student of Lomonosov Moscow State University. My question is that you've said, and you've provided an example of using machine learning with different seismic attributes. Nevertheless, there exist technologies that allow to get information about acoustic qualities of rocks, such density, velocities, and impedance. So my question is, can machine learning be more accurate with the data set of acoustic qualities and rock physics modeling?
That's a very good question. In fact, you're fundamentally talking about inversion, seismic inversion, and then the derivative products that people compute from inversion. You're absolutely right. In fact, that's what a lot of people want and need in a development setting, for example. It is very normal and routine, actually, to employ those inversion products in different, for example, in unsupervised learning, where you use different seismic attributes. They don't care what the attributes are. Whether it's inversion, it could be any attribute. And inversion is actually one of the most common ones used in the process in a lot of the derivative products. So a real issue, and I think what you were getting to, is how do you relate that the results from the sums or unsupervised learning into reservoir properties. Well, now there are more recently been a couple of papers published in the first break where one, they actually had well controlled and broke down those 2D color map. When I showed you those different neurons, they actually interpolated those to be 𝗥𝗱𝗏 and porosity based on the results from the self-organizing maps. And one of the attributes they used was inversion. Some fantastic results. Another one was done in Mexico. That one was done in the Barents Sea. The other example was done in Mexico, where they actually ran statistical analysis on how the neurons correlated to the reservoir properties in the well logs themselves. So you had statistical validation and trying to understand the reservoir properties. That was a very good question, because that's where things are trying to go.
Yeah.
Okay. Thanks. Yeah, thanks a lot for the answer.
Okay, let's see. We have another question about slide number 81, which I think wants a bit of clarification on just what exactly a neuron is. Maybe a little bit more explanation.
Okay. A neuron is nothing more than in unsupervised learning, which 81, while I was in the unsupervised part of it, it's nothing more than a data point that identifies a pattern or a cluster in the data. In other words, when you put all these data points in attribute space, or some people call it hyperspace, from a computer scientist perspective, you've got all these data points just floating out there. They've all been normalized to the same scale, and you randomly put neurons. They're just randomly situated in all these data points. The data points never move. Only the neurons move. And the neurons move around and with very simple math. In fact, you'd be shocked how easy the math is. And it moves around until it is kind of figured out a host that each neuron will identify a pattern or a cluster in the data. And that's all a neuron is. And then from an interpretive perspective, we can just highlight that neuron and it shows up in a 3D data set what data points are associated with that particular neuron or combination of neurons. Now, in supervised learning, a neuron is very different. In supervised learning, a neuron is a set of points that are weighted as you input the labels or descriptions, and they go back and forth mathematically, weighting these things until you come up with an answer in the model that's built. So the neurons are a little bit different depending on whether you're in supervised learning or unsupervised learning. Hope that answered the question.
Okay, thank you. Yeah, let's see. We have another question, which it says, how do we start learning to do this on the seismic data itself? So I think that may mean like what tools specifically. So that may give you a chance to explain the tool you've been currently using, the software. Which, by the way,
yeah,
I would just mention, we have 2 licenses to the Paradise software available for the students to access.
Yeah, and there's, you can use, there are different types of machine learning you can use on seismic data. I showed you seismic facies. You can also do fault delineation with the neural networks. In fact, what's kind of interesting about that, if you remember, I said that on supervised learning, you have to build a model. Well, in that example that we're talking about here, the model was actually built. It was built on synthetic data, and then it applied it to the regular seismic data. Those are supervised methods. Now, the unsupervised methods is where you put together a series of different attributes depending on what your geological goal is. Now, am I looking for lithology? Am I looking for fluid effects? Am I looking for structure? Well, it will dictate what attributes you use, because not all attributes are good for everything. And then you combine those through the process of unsupervised learning to hopefully help you define those features better.
Okay, well, thank you. Yeah, and as far as using, the Paradise software itself, just a message to the students that we do have a license available here in the Houston office, which you can access. We do want to make sure you understand the basics first, though. What we don't want is the students immediately leaping into doing all sorts of sophisticated things without having thought through the petroleum geology and the details of their area and so on. So let's see here. Somebody had a question about how can we learn more about algorithms to help interpret seismic data. So I don't know if that means like, where do you go to see papers on these algorithms? I mean, I think that's what it's kind of, what's the thinking behind these various algorithms, and where can they learn about the thinking that is behind them?
But, that's a good question. I've been asked that before, because there's not really one location to get a lot of that information. You have to, there's some basic books. You can get on the internet, and Introduction to Machine Learning Approaches can kind of give you a background. But as far as how the algorithms are applied, or the machine learning is applied to the geoscience world, really the only thing that's really been written on that is over the last few years in our technical journals. Interpretation, EAGE, First Break, Leading Edge. There really hasn't been too much up until the last few years. I would say about 10 years ago, you started to see a few papers, and really about 5 years ago, it really started to flourish more. I would encourage you to look at those. Now, there's a whole lot of different aspects to machine learning. For example, the majority of people tend to program in Python, scripting language. It's not the only one, but it's certainly the dominant one. A lot of the statistical approaches that I showed you are done in R, but there are other ones. SAS has different approaches. And certainly because, especially with neural networks, there's so much number crunching going on. Again, the math is very simple. A lot of number crunching. In fact, that's why machine learning has been given the connotation of a black box, because you input data, it does a lot of number crunching, and you get an output, and it is very, very difficult to understand how to get that output. And the way I always look at it is, if you were a machine or a computer looking at a human, they couldn't, and they gave you something and you gave an answer, they couldn't figure that one out either. How did you get that answer? Well, that's what it's trying to mimic. It's trying to mimic the human brain.
Okay, I think maybe we'll try one more question here before like a very quick break, and then we can come back. So this one is from one of our Evolve 2018 students, David Safransky, probably still up in College Station. And so he's asking about what techniques you would suggest for evaluating the uncertainty of the prediction. So it's like you're making a prediction, but I guess there's still a range of uncertainty. So I guess that's it's like you get a result, but then how do you gauge the range of potential error even in that result, I think would be the question.
In fact, I think that's ultimately where all of this is going. For example, Monte Carlo simulation. Any of us that have been around for a while and we have to compute reserves or resources, most companies today use Monte Carlo simulation, which is a type of reinforcement learning, believe it or not. It's a very simple force of reinforcement learning. And the answer from that is actually a range of answers in a distribution. P10, P90 distribution, you can pick a mean of that distribution or whatever you think is appropriate mean or a mode of that, whatever you're looking for. If in reserves, we quite often take the mean. But I think that the distribution of answers, potential answers, is the way things are going. A a lot of the results from machine learning today are trying to find specific answers as opposed to a range of answers. Kind of depends on what you're looking for. For example, a perfect example is a fault. If I have a machine learning algorithm that picks a fault, well, they can't tell you exactly where that fault is. And in reality, in geology, a fault is not a line, it's a gouge zone where rocks have been displaced. Well, we typically will calculate whether the fault is by probability. We're trying to find probability as related to the fault being there or not being there. We can't draw the line exactly where it is, but you can calculate a probability of where it should be. In fact, that's actually being done. That's most of all the fault picking algorithms from machine learning. That's actually what you're looking at. You're looking at the probability, not the actual fault plane. That's the direction I do think everything's going.
Okay, well, I think what we'll do, there's still a few questions. So what we'll do is we'll take a quick break. I know some of you, probably managers and others, have to go to meetings. So let me do a quick share of my screen. We'll do a quick closeout, but everybody who wants to continue, it's a very interesting discussion. I've got a few other questions. Hold tight. Let's see, wait a minute. Presentation go right here. Sorry. So we saw these. So anyway, so yeah, thanks. Those of you who are leaving, thank you for being here today. We're always looking for new and interesting topics. We are working on some of these right now. Petroleum geology of the Niger Delta, something to do with source rocks, probably a talk on fractals in E&P at some point. So stay in touch with us in those various media we talked about. If you liked what you saw today and want to support Evolve, we're always looking for companies to sponsor these student teams, whether one or more teams. So you can go to this location here. So if you're an oil company and you want fearless explorers working for you in the future and who appreciate what you've done for them, come here to this page and see about sponsoring the student team next year, as Mr. Forrest and I did last year, and he's doing again this year. Otherwise, if some of you want to come to the SEG website and just make a small donation, minimum $10, every little bit counts, please go ahead and do that. So we're going to close out here. And so speaking on behalf of our Evolve students, a very enthusiastic and bright group. And so speaking for them, we are not afraid of the future. We are the future. So we'll see you next time. Thank you. And we'll hold for a few seconds and then continue with the questions. Thanks. Okay, so assuming my producer gives me the go-ahead here, I think we'll continue with some questions.
Yes, of course. There's still people on the YouTube that are awaiting their questions answered.
Great. So here's a question from Miss Sarah Kalal over in Algeria. She was one of our students also. So our Evolve students, by the way, they stick with us. I mean, we build lifelong relationships in here. And her question is, how do the number of properties or inputs, which I think it's where you start doing your n-dimensional analysis, how will those affect our results? The number of attributes, I think you put in at the start.
Well, there's a couple things, whether it's, for example, in the SOM analysis, the number of attributes or maybe the number of neurons. Technically, there's no limit. There's a practical limit. For example, I guess working with that sort of approach for so many years, we know that if you're running the actual principal component analysis, you can put dozens and dozens of attributes in there. It doesn't matter. However, in the SOM, you typically, somewhere between about 5 to 10 attributes is ultimately what you want to use. And there's no limit mathematically. It's just from a practical standpoint, that with the seismic type of data we use, that's typically what we found the optimal amount. Now, the amount of neurons that you use to look at all that data typically runs between about 25 to about 100. Mathematically, you can have thousands of neurons. You can only have 4 neurons. But if you think about it, if I have all this data, the more neurons that I have, the more detail it's going to break out. And what we know is that when you put too many neurons in there, a lot of neurons aren't going to identify a pattern. That means you got a lot of wasted neurons. And you got way, way too much detail. There's the saying, you can't see the forest for the trees. There's so much detail, you can't see anything. And then on the other end of it, if you have too few neurons, then it's grouping things together so much that you don't see the geological features you're looking for. And one of the drawbacks to self-organizing maps early on is that people had no clue what range of neurons to use. But again, I guess through brute force and doing it for many years, we'll pretty much determine it's somewhere between about 25 and 100 neurons. And usually you'll do like 25, 64, and 100, and look at those results, and you start to hone in on what's the optimal number. It's kind of an interpretive process. Hope that answered the question.
Okay, I see we have a question from one of our students, Mr. Silas, over in Lafayette. Hopefully not too wet at the moment. Do you want to actually ask your question in person? Just unmute yourself and you can ask your question directly to Mr. Roden here.
Okay, hi, Mr. Roden. I'm Silas from the University of Louisiana at Lafayette. I think your presentation was really good. So I was wondering, I noticed that most of the online resources to learn about machine learning are mostly for general applications. So I was wondering if you could give a guide towards maybe courses which were more focused on seismic applications or geoscientific applications.
Yeah, you've got to get into our journals, geophysics, first break, EAGE, geophysical prospecting. These are really focused on the geoscience application of machine learning. Also, the different conventions all have workshops. Every one of them have usually more than one workshop on some sort of machine learning. You can get the abstracts from those presentations. Several companies have machine learning references on their websites that can truly help you try to understand some of this. But you got to remember that I envy all of you young folks, because this is this is extremely exciting. And how the application of machine learning, and we've seen some really, I call it profound interpretation things evolving. For example, seeing way below tuning, that to me is profound. Never been able to do that until the last few years. And there's other applications being done that makes us think. For example, picking faults in very complicated faulting regimes in thrust fault areas or strike slip faults or very complicated tectonic areas. It's helping us get a better feel on what the answers are versus just making an interpretation and hoping it's right. So I really encourage you to look at potential machine learning approaches and answers.
Okay, thank you.
Okay, I'm reading, this must have come from YouTube. Let's see, this actually talks about the accuracy and how successful you can be in a SOM analysis versus data quality. Maybe signal to noise ratio, what kind of ranges of signal to noise conditions have you worked in yourself? Yeah.
That is a really good question. In fact, you can apply that to any machine learning. If you have garbage in, you typically get garbage out, or you certainly have less confidence in the answers. One of the more interesting things about some unsupervised approaches is that, you know, when you analyze data and run it through like self-organizing maps, it doesn't know anything about the data. And it identifies noise. It's just another pattern in the data. I mean, it's just math. And it can, as I showed you, there was an example, it showed the acquisition footprint way down in the section that was never seen in amplitude data. It can see incoherent noise. In fact, several processing companies have been interested in these approaches because it helps identify noise in the data. It's just another pattern. But the bottom line is, if you have poor data, then the results tend to be not optimal. That's still an issue. But by the same token, they are using machine learning and processing to help get better data too, at least seismic data.
Okay, and I see a question from one of the other students. So we got Mr. Chisholm over, he's part of our Birmingham team in the UK. And since you're part of the Evolve students that are part of this actual Zoom piece, I'll give you the chance to ask your question directly to Mr. Roden. If you want to turn yourself, your microphone on.
Hi, I'm Chisholm by name from University of Birmingham. That was a nice presentation. I was just wondering if machine learning, if you could say machine learning is just for us geoscientists, or is it just for interpreters? Because personally, I'm into seismic processing, and I know I see on some on online where you have some companies who tout machine learning as the next big thing and all that, but I tend to see it mainly get towards interpretation and not seismic processing and all that. What's your experience on that?
Yeah, that's a good question. There's a lot of applications of machine learning in processing. In fact, I would argue that some of the early uses of machine learning actually was in processing. First breaks. They've used neural networks for picking first breaks for a long time. It's been at least a couple of decades, I know, that they've been doing that. And I think data processing is uniquely qualified to have machine learning applied to it. And it is definitely happening. There's no question it is. And I think you're going to see a lot more of that. In fact, sometimes you may get the lines blurred between processing and interpretation because of some of the machine learning applications that are evolving. So that's a good question, but absolutely that it's being used significantly in the processing world.
Hello, Mr. Roden. Can I ask a question?
Please go ahead.
Sure.
Introduce yourself to Mr. Roden, yeah.
Yep. Hello. My name is 𝗥cie𝗱𝗀𝘆. I'm from Ukraine, from Kyiv National University, Petrokurs team. I just want to ask you, is there any examples, I don't know, approach to use machine learning for specific values like, I don't know, piece of G, where the result is dependent on how you interpret this, and each dynamic values is dependent on the, I don't know, structure or environment where you are looking for?
That's a very good question. And my colleague Mike Forrest and I are in the middle of a lot of that as we speak, because most companies will look at, when they're doing a fundamental probability of geologic success, they tend to look at 4 to 5 to 6, it kind of depends on the company, various geologic chance factors. And the thing about those geologic chance factors is you have to assume that those are independent variables. At least that's how I've always thought about it. And you come up with a risk of like source, migration, reservoir structure, these sorts of things, and you multiply those together and get a piece of G. And now what we do is quite often we'll take a P10, P90 range of each of those and do some Monte Carlo simulation also at times on some of these sorts of things. But I think what's going to happen is that as these machine learning algorithms they're designed to handle non-linearities in anything. And there are a lot of non-linearities in risking. And we tend to make things much more simpler than they really are. I think that you're going to start to see there are different approaches in computing these P sub G that are not just simply multiplying these 5 chance factors together. It can be a very, very involved set of parameters applied in a machine learning approach that ultimately will give you a range of probabilities. Especially when you start adding things like direct hydrocarbon indicators, which are very different than geologic chance factors. They're extremely nonlinear, they're extremely interdependent, as opposed to independent for the chance factor. Very different sorts of phenomena. Machine learning is going to help us define that, I think, because it can handle these nonlinearities in data in these crazy interdependencies that we don't understand. That's a really good question. I think it's something you should figure out. You'd probably do pretty good.
Yes. Well, of course, we've been doing volumetrics and risking with the students, and we do have access to the Rosen Associates Risk Essentials, so that's why they're kind of up on, and we talked to them about, well, some of these things are quite ambiguous. You know, is something a 40% chance of source or 50% chance of source, you know? So let me see, I think we've addressed all the questions, but let's see. And I guess what I would say is if anybody on YouTube or Facebook has any more questions, kind of last chance. I mean, now I do have one question, and maybe I'll have a career comment afterwards, picking up on what you said. Of course, you know the Paradise software, you know the Kingdom software, and you know when we go to the final prospect maps, how important those fault polygons are for calculating, of course, where the leak points are, etc. So, of course, you know, all these faults being created out of these algorithms is one thing, but how do we are we going to head towards where we actually will have some fault polygons created out of that, which would be a huge time saver if we could go to that next step and not have to, because right now we still have to look through every one of those, right, and check it and be sure. Right. And so is anybody working on actually shortening the process to getting credible fault polygons from those faults?
In fact, Alan, I think that's where the future is. What the future is going to be these workflows where you're going to have, you can set up a whole set of interpretive functions. Some of them may be machine learning, some of them may not be. For example, I may do some sort of a signal to noise analysis, and based on that, it'll automatically do a bandpass filtering, and it'll automatically resample. And then you're going to take it into calculating a bunch of attributes, and then you may do an automatic. This can be automated. There is no reason in the world this stuff can't be automated. Now, you might want to stop it at different times to QC it, and sometimes you're going to have to make a decision. But a whole lot of this can be automated. And I absolutely believe that's the direction things are going. I mean, why should, as an interpreter, I be limited in my workflow because of Petrel or Landmark or Kingdom? They do something a certain way. Why should I be limited to that? Why can't I do it a different way? I mean, a lot of smart people out there, and all you have to do is, and we have the technical capability to do that. It's definitely, I've seen it. It's happening. It's evolving. And you can automate all of these processes, and then stopping it, obviously, from an interpretive standpoint in different places, because you may have to make decisions. But I think that's absolutely what's going to happen.
Okay, well, good. I agree with you that I think, we've got all these tools, And you mentioned 3, and there's of course a whole variety of other specialized tools. And personally, I use the term the glue, because we've got all these tools and algorithms and everything, but the real key to the future is going to be what's our head. It's in our heads, and I call it the glue. You take these pieces that anybody can get, but what is truly unique and will give an individual competitive advantage is how you figured out to link and use all these pieces of information and tools and so on. So let's see, looks like a couple more questions. Okay, let's see. I guess some people are interested almost like in a follow-up lecture from you. Let's see, a follow-up lecture on basics of interpretation to help define which attributes to use. And I do know when we took the course there, Mario Jesus and I took the course here, that you've got that little chart. Do you recommend, in fact, I got it on the wall here, in different situations, which attributes are best? So I think in part, someone's inviting you to come back and give us a second talk at some point. So
I'll be glad to.
Yeah, and I don't know if you want to make a quick comment. I mean, obviously that's a complex.
Yeah, I mean,
your chart is
that is a very good and question, and there's but I certainly don't know all the answers, because I can tell you there was one of those papers that was just published in the first break, and they were looking at a field, Wisting field in the Barents Sea, and they had several wells, and the 3 attributes they used were inversion, amplitude envelope, and instantaneous Q. Just those 3. And they use those 3 attributes in an unsupervised method. And what they, in the inversion was very good. They were pleased with the inversion, but when they added the envelope and especially the instantaneous Q, the porosity and the volume of clay were defined in much more detail than they ever saw before. And they knew the answer. They actually had cores in one of these wells. And in particular, one of their reservoirs was defined in much more detail. And and I was very interested, you said somebody is going to talk about fractals. There's something that we're seeing in the interpretation of, for example, in self-organizing maps. There's something called the theory of self-organization. Mm-hmm. And we see it in a lot of this in geology. And for example, if you look, not in geology, if you look, you have a flock of birds, and how you have all of them, they move in rhythm and synchronous. There is no one bird controlling that. They have self-organization, or a school of fish, a whole bunch of small fish. There is no one fish controlling that. There's a self-organization going on. Crystallization in the earth is self-organization. Well, there's something that relates to that in interpreting our geology, the depositional patterns, the fluvial systems. There's a self-organization going on, and self-organization neural networks and self-organizing maps brings a lot of that out. You see that 2D color map. There's a reason those neurons are where they are in there. They're organizing in certain ways, and they're seeing the geology in certain ways that have been laid down in self-organizing principles. It's really exciting. And like I said, I wish I was younger, because man, this is really neat stuff.
It's nice to see, and the students see the passion in all our mentors, and it's nice to see it again in your responses there. They've got the pleasure of working with Mr. Mike Forrest, who's passionate, as are many of the other mentors. Let's just see here. There's a couple of other questions. I'm going to see one. I'm going to read them to myself first. Yeah, there's a question from Bayero University, Kano, Nigeria. How can machine learning be used to delineate sedimentary attributes and sedimentology. I think you touched on that actually in the beginning in one of your slides, but maybe you want to expand on that.
Yeah, there's different ways. A lot of for example, in the unsupervised, depending on what sort of attributes you're using, you can select attributes that are very, very good at defining stratigraphy. You might be looking at, cosine of the instantaneous phase or instantaneous frequency, instantaneous phase. A lot of these attributes that are very good at defining stratigraphic variations. Those would be very good at seeing that sort of thing. If you're looking at something that wants to see amplitude variations, you want to look at something different, maybe acoustic impedance or envelope or sweetness or some of these sorts of attributes. So it just depends on what you're looking at. Instantaneous Q is very sensitive to porosity. So there's a lot of different, you want to use a set of attributes that are good for the geological problem you're trying to solve. And of course, there are many different types of inversion and derivative products from inversion can put it into these machine learning approaches.
I think sometimes the questions are a little bit aimed at kind of what's the shortcut, like what's my attribute to go, find all the oil easily, et cetera. And I mean, of course, we know with our years of experience that, there are no easy answers to some of this stuff. And, one thing I will say, this goes back to the pie chart that we put together, that there is nothing that beats using these and building up the case histories in your own head. So that's when we say that 50%, that means, sure, know the tools, hopefully have effective delivery mechanisms, but there's going to be no shortcuts other than you spending a lot of time with a lot of data sets and building your own case histories in your head. That's the ultimate way you're going to really get to use this effectively, whether it's for sedimentary analysis or whatever, defining contact or other things.
In fact, Alan, I think that the use of machine learning interpretation, you're going to start seeing some profound results. And you may not understand when I say profound, what does that mean? I'll give you an example. There is, several years ago, there was a study done at the University of Ontario. And they went to the prenatal ward in a hospital where premature babies were born. And they put a sensor on every one of these babies that was fed into a machine learning algorithm. And what they found is that when they were reading these readings from these premature babies, the thing they have to worry about is a baby getting an infection. That's what you have to worry about for these premature babies. Well, they were feeding all this information to this algorithm, and they found out that they were actually identifying up to 48 hours before any of these babies showed a symptom of having an infection, that they were going to get an infection. And they did this over and over and over again to the point that, and they couldn't explain it. They didn't understand why. Now, there is a scientific reason for it or a logic for it, but they didn't know what it was. And it got to be so accurate that the doctors and the nurses, when that algorithm said this baby is getting ready to have an infection, they would start treating them immediately. That is profound. You're using the machine learning that's seeing something in the data that you're proving over and over and over that it's telling you the truth. Now, not everything is that simple, but that's profound. And I think like seeing thin beds and some of these sorts of things, that's why I'm excited about this, because I think you're going to see that in interpretation. I definitely do think that. You'll get better interpretations ultimately down the road.
That's great. So let's see. There's one question I think I'm going to answer is for you, but it's what advice would you give a young geoscientist advice to learn about machine learning or integrated softwares like Petrel? So I'm going to give my answer. You can give yours if you disagree. I'm going to say both. And this is, evolve is multidisciplinary. So, what should I learn? Geophysics, petrophysics, engineering, all of the above. Now, the reality is you can't do all simultaneously, but the point is over the course of your career, you cannot do a good job at understanding Mother Nature if you're in a box, that you only understand petrophysics or you only understand engineering. So to me, it's like we've got these new tools. So of course, go keep learning your Petrel. That has certain, or Kingdom or DSG, learn all those, but use all these other tools too. I mean, over your career, and we're talking decades here, as students know, you want to learn about all these tools and technologies and how you bring them together in your own head. That's your unique value proposition. Now, I'll let you disagree if you do. You probably won't, but let's see what you.
No, I'm not. How can I disagree with that?
Yeah. But really, I mean, there are certain settings in companies. I've worked at some of them, and I'm not saying they're great companies, but they do encourage you staying in a box. And there is a reason, because, I mean, we all have limited capacity in the short term. So they don't really, if you're the petrophysicist, they don't want you spending too much time reading papers on other things. So early in your career, people will tend to put you in a box. And so that's what you have to do if that's what your employer is paying you to do. But over your career, you should constantly learn about all the other disciplines.
So another aspect of that, Alan, that is that it's a challenge, I understand, in several universities in getting machine learning courses. I know for a fact that a lot of universities are struggling with, where do I put machine learning? Is that in IT department? Is that in computer programming? Is that do you have it in each individual discipline like geology or geophysics, or do you have it in engineering? I know that there's a challenge in some universities in just getting courses that have any relationship to how you want to apply it. And that's where you have to go outside, because that's where you have to go. It's evolving. It's very interesting.
So what I would like to do is to come back to a point you made, because these are all students, they're all going to be looking for jobs. Some are already looking for jobs, actually. And I wanted to come back and maybe make a few editorial comments on something you talked about, which is that, these new technologies, they're not going to need fewer geoscientists. They actually are going to need more. Now, I will tell you, and this is where I'm getting into my editorial mode, that many of, I'm going to call them the money people, whether you call them private equity, they love a story of getting rid of people. And so I hope there aren't too many of them listening in here, or I'll be in trouble. But they love the story of, hey, we get rid of people, we save money. And so they love machine learning as a personnel reduction mechanism. And as we say, those of us who really know Mother Nature and the real data sets know that, no, you're going to need more geoscientists to integrate all these things. So to work with the Petrel or the Kingdom or the DSG and these other tools and learn all these things. So that, I'm glad you made that point, because there's a future for these students, but they've got to embrace everything, not just stay in a little box.
In fact, I actually have a very long version of what I gave today, is where I have statistics on the amount of people in the world, the consumption of power, the demographics of geoscientists in the world. And there is no question, next 5 years, 10 years, there's going to be a shortage of geoscientists for finding oil and gas. And oil and gas, whether, renewables are evolving, but they're still not projecting them to take over for another 20, 30 years, even to get to halfway point. And the consumption at the same time is increasing across the world. And the people coming into the industry today, they're my generation's almost gone. That's the big bubble. That's the big demographic of the baby boomers. We're almost all gone. And certainly in the next 5 years, there are not going to be many of us around. Of course, Mike Forrest will be here forever, but that's beside the point.
I was going to say he's our gold standard. So I like to say that
That's right.
yeah, we still got another 25 years to go, some of us, because hopefully we'll be around when he'll be around. So you haven't gotten rid of some of us yet, at least.
There's going to be a need, and that's the other reason that we need to implement machine learning. We have to be more efficient 5 years from now, 10 years from now than we are today. We have to be better. And like I say, I think it's an exciting future, to tell you the truth.
Okay, well, I think that's the questions, and it's about 10:30 Houston time. I think it's been a great discussion. And actually, I'm going to see if our producer, Mr. 𝗥cie𝗱𝗆𝘆, can unmute himself. So are you there? Just want to check on a couple of things.
We answered all the questions, so we're good to go. A lot of thank yous going to Mr. Roden and to you, Mr. 𝗥cie𝗱𝗆𝗆. So thank you from me too.
So I did want you live here because I'm going to read something, and I'm going to want Mario here to confirm that I'm not making this up. So I should tell you as context, you see, I spend all this time hounding the students and, making sure they come to meetings. We have meetings every Friday, and then telling them, hey, your volumetrics are off by a factor of 10, etc. So they're used to me just driving them, and I think they think of me as very unpleasant, you see. So I see someone here on YouTube, and this is where Mario's going to confirm I'm not making this up. In fact, take a JPEG of this. So someone who asked a question says, by the way, very pleasing personality of the moderator. And so you see, students, you may not appreciate me, but apparently the YouTube audience does. So Mario, do confirm I didn't make that up, right? That's written in the chat.
I did. Yes, she is right there.
Okay, there we go. So anyway, well, again, I want to thank Mr. Rocky Roden for taking your time. I think it was a great back and forth. Mr. Forrest, I think, was listening in. Speaking of him, I think he had to drive somewhere. He let somebody else drive, and I think he's been following us on his phone. And it would have been nice to have him participate. But I think we should think about a part 2 on this, like maybe pick some of these questions and come back, and maybe a little panel discussion too.
Okay.
So again, thank you very much. Again, another digital round of applause. And then after this, we go to our Friday office hours with the students. So again, thank you very much.
Thank you. Enjoyed it. Take care.
Okay, we'll talk to you next time, and I'll stay on, and Jesus and Mario will stay on with the students.
Later, Internet.
Yeah.